Entropy. When I think of entropy, I think of my 4-year-old daughter. If she comes into a room, no matter how clean it is, pretty soon it's chaos and disorder, and we've got to go in there and kind of fix everything up and try to straighten it out. So basically, entropy is the amount of disorder within a system. So let's look at an example of entropy. Let's say I've got water, and I've got that water frozen in a nice little ice cube, okay? And this ice cube has a lot of order and a lot of structure. And all these molecules are held together in these very tight, precise bonds, okay? Now if we let that ice cube melt, it's going to gain entropy. It's starting to gain energy, and it's starting to move around, and it's losing that order and that structure. It's moving towards disorder. And so now our ice cube, I'm going to put it into a little cup, is going to become water with more energy and more motion and more disorder. If we let that continue to evaporate, it's going to turn into water vapor, and it's going to become all the molecules in the air, in water vapor. And that's got a lot of energy and a lot of disorder. And those molecules are going everywhere and bouncing and colliding into other things. So that is a system with a lot of disorder, high entropy. But as the water is going from order to disorder, that energy is also causing an increase in entropy in the air molecules around it. As the ice is melting, the air around it is getting cooler, and that's causing a decrease in entropy. And as the water evaporates, that evaporative cooling is cooling off the air, which causes a decrease in entropy in the air. So entropy can go in two directions, and oftentimes it goes in two complementary directions as one thing heats up and another cools off.